very simple. It's just a toilet that moves underwater, and with the new shape, we are able to create thermal pleasures.
Every time?
Every time.
For as long as you like?
Yes, we have a powered run here of 150 meters, but we can build as long as we want. Okay, so this is the control panel. We have information here that shows the height of the wave, the speed of the wave, and every parameter that, from an engineering point of view, is critical for the functioning of the machinery.
And you just start it by pressing that red button?
Yeah, and you stop it pressing the button.
So I've searched a bit at home. I've never tried anything like this. Give it a go.
Oh. Any surfers here? No. I surfed once or twice. When I was your age, I guess. It's kind of interesting that they have basically a wave pool, a very long wave pool. It's in South Wales, I believe, of all places. Yeah, pretty cool, isn't it? What else have we got? This is kind of interesting from a couple of...
Watch closely. This is Britain's Andrew Cotton harnessing a monster wave that could be the biggest ever ridden. He held his position for 10 seconds in an attempt to enter the record books.
I'm sort of very focused on actually what I want to do and where I want to be on the wave. I actually want to surf the wave, I just want to like hurtle down out of control. When you do things like this, it's fine line with things I surf all the time.
It's a fine line between clever and stupid, right? Isn't that Spinal Tap?
It's not ideal, but yeah, that's just how it is.
See it again.
Amazing.
And the size of the wave hits you. Andrew rides at 80 feet. That's higher than the Angel of the North and nearly half the height of Nelson's Column. The current surfing record of 78 feet is held by Garrett McNamara, seen here off the coast of Ireland with Andrew Cotton last year.
The vision is to surf the biggest wave in the world. And very, I haven't actually been too much coming, but no doubt when the summer comes, they'll probably be back on the beach lifeguard and back on the building site.
Atlantic storms and the unique geography of the coastline in this part of Portugal have produced gargantuan waves. Surfing judges will now watch this footage and decide whether Andrew Cotton has set a new world record or not. Ben Hagan, BBC News.
All right. So you can see that one of the themes today might be waves. I wonder if this... I don't know if this one works still. Doesn't look like it might. And if you've ever flown and sat next to a window on the wing, perhaps you can't see it very well, but you can see a condensation trail on top of the wing from a change in phase, presumably by low pressure, causing expansion, causing cooling of the air, which then condenses the water out of it. You see it just coming up right over the top of the engine cowling and over the wave. So the topics for today that we'll discuss are, don't do that. Are to talk about waves. First off, we'll talk about phase behavior of fluids. We'll talk about viscosity, and we'll talk about surface tension. So that will kind of round out our discussion on fluid properties. I think everything is under control, everything's uploaded. The recorded videos from each class go on usually before noon, and so they're on, certainly the first two are on the course resource web page if you look for it. For some reason my website went down yesterday briefly, but last Wednesday's material is online, and so if you want to be able to view it, you can. and all the things we talked about. And if you're here, obviously you don't need to necessarily do that. If I go back, the problem in doing this is that something is probably, is it running in the background? Yes, we don't want it overprinting what I'm talking about. Fluids in the news. Anything about Hurricane? It's not Damien, is it? What is it? Dorian? Dorian, yeah. I think of Darien Gap, which is in Panama, right? But actually, no. So Florida, I think, is bracing for it, for landfall, I think, on Monday. But nothing much in the news. So there's usually some fluid mechanics stuff in the news, but maybe not so much today. All right. So we can probably get rolling, mindful of the fact that some of this stuff is off the side of the screen. So as I mentioned a second ago, what we talked about last time are these individual components here. We talked about some definitions for fluids. We talked about if you want to add apples, you have to add them to apples. So equations have to be dimensionally homogeneous. We spent a bit of time on it. The significance, of course, is that can't tell you whether the equation's right, but if the units are not homogeneous, it can tell you that certainly that equation is wrong. And so it's a useful check on your calculations to be able to make sure that you're not wrong rather than being right, for instance. We talked about significant properties, and for us our significant properties were density, dynamic viscosity, and modulus, or stiffness. And stiffness is just the reciprocal of compressibility. We almost finished that, but didn't quite. We talked in terms of definitions of mass. We defined equations of state for gases through the ideal gas law. We started briefly talking about compressibility, but maybe didn't get all the way through it, other than to say that compressibility is just an index of how resistant a fluid is, whether it's a gas or a liquid, to change in a volume. If you have to apply a large stress, change in pressure to get a big change to get any change in volume, then it's not very compressible. It has a high modulus. This magnitude would be large because this has to be large to get any significant change in density, and therefore the compressibility, which is just 1 over this by definition. This is units of stress. This is units of reciprocal stress, 1 over stress. Allow us to be able to say something about the fluid. So liquids are low compressibility typically, and gases are relatively high compressibility. The one thing that we perhaps should clean up before we move ahead is just to briefly revisit that, to talk about compressibilities of gases. And we made the point that gases we can define in terms of, I guess this is a remnant from last time. Gases we can represent by the ideal gas law. And if we want to be able to define compressibility, as we've defined before, either in terms of the pressure change you have to get a volume change, or the pressure change you have to get a density change. Obviously, if you have the same mass in a smaller volume because you compressed it, the density is increased, and that's the reason for the difference in this, the sign convention. Increased pressure gives you an increased density. Increased pressure gives you a reduction in volume. You want this unit just to be a positive unit. It's always a positive unit. If you want to define the compressibility for a gas, then you can rewrite this expression here just by taking this term and putting it on the top, which is what this is, and then try and figure out exactly what each of these individual terms are. This term here we can get merely by taking the ideal gas law and dividing by density and density, which kicks this out, and then taking the derivative of this, which is RT, which is constant. And we can also rewrite the ideal gas law in terms of density. So in other words, pressure being equal to density times gas constant and temperature. We can rewrite in terms of this, which is just density being equal to pressure over two constants. So if we substitute this term here in for this, and this term here, we end up with a constant cancelling out a constant, and you get the surprising result, which we'll use today, and that is that the modulus, the stiffness of the air, is just equal to the pressure. So we know that the pressure here is atmospheric, 101.3 kilopascals. So the stiffness of air has to be exactly that, and the compressibility of air is 1 over 101 kilopascals. So this is the only result from what we've talked about this morning that I want you to perhaps be mindful of, because we'll use that. Okay? So in terms of what we want to talk about today, I said we'd discuss 4 things as we in the run into this. We'll talk about wave speeds, relevant because you listening to me, you hear me at the speed of sound in air, and of course that is controlled by the wave speed. We'll talk about viscosity of fluids, vapor pressure in transformation of liquids to gases, and we'll also try and talk about surface tension. So we'll talk about those 4 things. The reason that I wanted to go back to talk about compressibility and stiffnesses is that wave speeds are related to that. You can think of you hearing me as being the same as a locomotive shunting into the back of a train full of a whole bunch of carriages. It shunts into the back, and there's a wave that goes along that, boom, 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 as the couplings of all those wagons join. And that's like a wave transiting along, in this case, a series of rail cars, the same as me hitting this bench. If you put your ear on the front of the bench, you'd get hit in the ear as this bench moves, but it's a dynamic wave that passes through it. And so waves have a variety of different forms. If we look at compressional waves, then we can define the wave speed as being equal to, at least in a fluid, this is the shear modulus, and in a fluid the shear modulus is 0, and this just becomes what we've defined as the bulk modulus divided by the density, all square root. And so this would be the compressional wave speed in air or in a solid. And so we can use that expression to calculate exactly what that would be. So this is the same as an earthquake, and that's the example that I'll use today, is to look at earthquakes which cause body waves to come, shear waves to occur also, which we won't talk about so much, but also can cause tsunami to develop as well. If we look at, for instance, actually it might be worthwhile just doing this, mentioning what these wave speeds are first. So this is the wave speed we get for a compressional wave from an earthquake. Happens 200 kilometers away. It takes some time for it to reach us. The time it takes to get here is controlled by the velocity it travels at. If we look at a different kind of wave, the celerity wave is not this P wave, this compressional wave, which is by hitting something. It's something that occurs when you disturb a fluid, and the fluid actually just rotates at the surface as this wave physically transits from one location to another, travels at this velocity. It's not the same as if you shouted down here, or if you shouted here and listened here. That would be controlled by this acoustic wave. And so what we'll do is realize that these waves equations are slightly different. The expression that we'll use for the celerity wave is this. We actually talked about it last time. You might remember that we talked about Bernoulli's equation being equal to the two terms being this, and we took these two terms divided one by another to show that since these were in units of length, velocity, gravitational acceleration, and elevation, since both of these are in units of length, we could divide it by one another, and we'd get a number which is called the Froude number, which we'll introduce in more detail later, but it's equal to the velocity divided by gravity times some length scale, square root. And so this, if you look at this expression here, this is actually the equation for the velocity of a shallow water wave. It comes out of this, doesn't really matter why it comes out of this. It becomes important for us to deal with because this represents the velocity of a wave. And so when we look at surface flows with a free surface, the rate at which you can signal what's going on in the system is controlled by this wave velocity. Information can't reach you faster than that wave. You can't hear a sonic boom faster than that wave arriving. And so it's an important feature in controlling this. And so if we were to look at some different systems, and maybe I can do it here, if we look at the wave type, if we look at the modulus, and if we look at wave speed, and we look at these three different things. If we look at, for instance, we're going to look at an earthquake. So we're interested in, for instance, looking at the wave traveling in rock. And we'll call it the P wave. Modulus of rock is typically something like 10 to the 10 pascals. You don't need to know that, but this is newtons per meter squared. And so if we do the calculation, I guess I'm running out of space, but if we do the calculation of the wave speed being equal to 10 to the 10 newtons per meter squared, it's going to look like this. Divided through by the density of rock, which is, well, let's make life easy. 2 times 10 to the 10 divided by 2 times 10 to the 3 kilograms per meter cubed. Whole square root. We can maybe get rid of these 2's. And this becomes, if I write it out, it's going to be 10 to the 3 over 10 to the 10, so that's 10 to the 7. So that is 10 times 10 to the 6. Newtons are kilogram meter per second squared. And so if you start crossing things out, you'll end up with units in here of meters squared per second squared, square root. And so this ends up being the square root of that. This is in meters squared per second squared square root. And the reason for doing this is that this equals about square root 10, which is about 3. And this is square root 10 to the 6 times 10 to the 3 meters a second. Meters a second to miles an hour. Well, this is 3 kilometers a second. Meters a second to miles an hour is roughly a 2-to-1 conversion. So this is something like 6,000 miles per hour, if you need it in miles per hour, and that you do. And so it gives you some idea of the velocity of sound in rock. So it's about 3 kilometers an hour. So if we do that for this, this is 3 kilometers per second, rather, right? KPS. If we look at water, we could do the same thing. The modulus of water is of the same order as rock. It's something like 1 or 2 gigapascals, so it's something like 10 to the 9 pascals. I guess I might put in density. So density of rock was 2,000 kilograms a meter cubed. For water, it's one number you will want to know is 1,000 kilograms per meter cubed. And so if you do the math with that, well, I can do it up here. So it's going to be 10 to the 9 divided by 10 to the 3. I should put the units in, but you know the units are pascals and kilograms per meter cubed. And so this ends up being 10 to the 6. Square root, and it's meters squared per second squared. And so this is like something like 1,000 meters per second. So roughly right. I think it's a bit less than that, but it's of that order. So it's about 1 kilometer per second for water. So it's slower than rock. And if we look at the velocity in air, then we know the modulus is equal to atmospheric pressure. So that was our first calculation today. The modulus of air has to be whatever our atmospheric pressure is. So it's about 10 to the 5 pascals. The density of air is about 1 kilogram a meter cubed. And if you look at the square root of 10 to the 5 divided by 1, it's the same as 10 times 10 to the 4, which is the same as 3 times 10 to the 2. So it's about 300 meters a second. You can confirm that yourself. So this is about 300 meters a second. We said that miles an hour is something like double that. So it's about 600 miles an hour, which is about right. We know that planes fly at about 500 miles an hour. Commercial planes, they certainly fly less than the speed of sound. They don't break the sound barrier because you don't reinforce them to make them strong to be able to do that. And so the idea is that these have different velocities. So these are the velocities for transmission in a complete medium without a free surface on it. We made the point that the celerity wave is something that is controlled by the depth of the water and gravity only. It matters what planet you're on and how deep the water is. And so if we look at the celerity wave, fancy word for a surface wave, it's not controlled by the modulus, but if we do the calculation for this being equal to gravity, which is 10 meters per second squared, roughly 9.81, and for, say, a kilometer deep ocean, which we'll use in a moment. So if this is times 10 to the 3 meters, and we take the square root of this, it comes out rather surprisingly that this is going to be 10 to the 10 to the 4. This is square root 10 to the 4, which is about 100 meters a second. And so this means that the wave far into the sea, where it's actually where the depth is relatively small, where it comes on shore, where if we're using a kilometer as being the depth, then the velocity of that wave in the ocean is traveling actually quite fast. It's traveling at 200 miles an hour. So not a trivial speed at all. So the reason for introducing this is that, one of the ways that early warnings happen for earthquakes is that if you have an earthquake offshore, then the time it takes to reach you, if you're, say, 100 kilometers away, and it's traveling at 3 kilometers per second, is going to be 30 seconds. Right? And so if you can detect an earthquake by having sensors very close to where it happens, then all of a sudden, if you telemeter that information onshore to where the seismic shaking is going to arrive, you potentially have 30 seconds advance time to be able to get ahead of it. The wave will then arrive 30 seconds later. But if it's an earthquake that causes a tsunami, so you get the slipping of the plates, you get one plate going up relative to the other one, it lifts the water up on one side relative to the other one, so you have a water cliff, can't sustain that water cliff, and the water cliff dissipates itself as a tsunami that travels towards the shore. And so if you look at, for instance, the most recent major tsunami was the Tohoku, the East Japan earthquake of March the 9th, 2011, which occurred because a plate boundary offshore, which you can see roughly here, flipped. This was the source of the event, which caused a tsunami to actually go onshore as a result of this. And we all know that the results of that, of what happened, were that 15,000 people died just by, not from the earthquake shaking itself, but from the effects of the tsunami. And so if you look at early warning systems, the P wave arrivals will arrive 30 seconds later, we said, depending on the velocity we use. It turns out that the waves that do all the damage are not the compressional waves, but it's the skipping rope wave. If you put a skipping rope on the ground and shake it from side to side, it's that distortional wave by shear shaking that causes all the damage. But if the tsunami is moving at 100 meters a second, and it has to travel 100 kilometers, so that's 10 seconds to go 1 kilometer, 100 seconds to go, so 100 meters a second, so it means it goes 1/10 of a kilometer in 10 seconds. It takes 100 seconds, is that right? 100 meters a second, so 1,000. So it takes 10 seconds to go a kilometer, it takes 100 seconds to go 10 kilometers, it takes 1,000 seconds to go 100 kilometers. 1,000 seconds is something like 18 minutes, right? 1,200 seconds is 20 minutes. So this gives you about 18 minutes before you get the arrival. And so if you look at the events that occurred in Japan during this, and we've got it somewhere. Where's Kamaishi? So this is a well-known video from Kamaishi. Oops, I didn't mean to do that. And so this is immediately after the event. I'm going to set my timer for each 5 minutes to remind me to look at it. So this is the time of the earthquake. The shaking stopped, so it's a few minutes after the earthquake, I guess. I'll turn it down. I'll mute it. And you see some boats going out of the harbor. And this is the time, maybe a minute or so after the shaking. People are filming this, I think, from a high-rise building or a parking garage that has stood up. And now what's going on is we'll just go on through our class while this unfolds, and we see the tsunami roll in as a result of this shaking. So nothing's happening for now. We'll come back and revisit this. I guess the other things to look at are that it's clear that the devastation of this was quite significant. This is a year later on the east coast of Japan. After this would all have been populated. It was in March, almost a year to the day after the event, on a cold March morning. And you can see that just this inexorable flow of water as not a breaking wave like we saw in Portugal, but as just an inexorable flood that moves in to the shore, basically moves everything off its foundations. This is a 4-story school that survived. The survival method, of course, is to go up to the highest elevation you can find. Highest elevation of this school was the 4th floor, which survived, but the first 3 floors did not. So you see the damage. The other thing, which was the first figure we saw here, is that I'm sure it's on the phone now, but this is the little device that gives you the early warning. So you record the earthquake on the seabed offshore, you telemeter the information onshore, you have 20 or 30 seconds to be able to get out of the building after the alarm goes off. And as I say, this is the building afterwards with the damage in it, but I think on the campus of this university, Tohoku University, everything survived except for one building, which was ultimately later demolished. And so anyway, so the importance and maybe the significance of talking about things like wave speeds. Okay? So, we'll let Kamaishi go off in the background. We said we were going to talk about 4 things. We got through one of them. Wave speeds we've done. We're also going to talk about viscosity in fluids. And so, actually I'll prefer to do it this way. I'm going to do it this way. So we are 1.3, right? And I'm going to talk about viscosity. So viscosity is a measure of how easy it is to shear a fluid. And a typical experiment is to take a fluid that is between 2 parallel plates, one of which is fixed, and one of which we move by applying a shear stress to it or a velocity in the x direction. And we assume that as we shear this top plate relative to the bottom plate, then it carries the fluid attached to this top plate with it at the same velocity as the plate. So if we draw a profile, a snapshot, if you like, of the velocity as a function of time, or space rather, then the velocity at the top here is the velocity x, which we have at this location. But as we go down through the fluid, the steady velocities due to this shearing diminish as they reach this lower plate to which it's fixed. So you can think of the fluid as being fixed to the top plate, fixed to the bottom plate. The top plate moves, and it's just like shearing a deck of cards, that these all shear relative to each other. And viscosity is just a property of Newton's law of viscosity. We will use Newton's law, second law a lot, but this is of viscosity, which says that the shear stress that you have to apply to shear the fluid is proportional to the viscosity, dynamic viscosity, multiplied by the velocity you apply in the x direction relative to the change in velocity in the y direction. So this is the x direction, this is the y direction. If you like, 5 minutes are up. What's happening in Kamaishi? It's still running, right? Hopefully it's still. Yeah, 5 minutes, 42 seconds. Still no wave. No incoming wave. So we're going to check our predictions. Okay. And so this we can measure. We can apply a stress. We can measure the velocity we get. So we'd know this and this. We'd know the thickness of the fluid we apply it to. And so as a result of that, we can get the value of viscosity, which is defined as mu, which is the dynamic viscosity. And the units of viscosity are Pascal seconds in our world, which are the same as newtons per meter squared times seconds. And so physically what viscosity means, or what Newton's law is, it's Newtonian fluid. So a Newtonian fluid is one where if you take the fluid and you plot the shear stress, which we're calling tau, and you plot it against the shear rate, which we'll call change in velocity in the x direction with change in the y direction. In other words, this slope here, you can think of that as this. So this is dy, and this is dvx, if you like, right? Those two. So a Newtonian fluid is one where if you have a particular shear stress that you apply, you get a particular shear rate, which I'll call, I won't call it gamma. I'll call it shear rate 1. If you double that shear stress for a Newtonian fluid, you double the shear rate. So in other words, SR2 is equal to 2 times SR1. Not all fluids are Newtonian. This would be a Newtonian fluid. Some fluids, for instance, are thixotropic. I guess I don't, why is this? I can't change my color right now. And thixotropic fluids would be, for instance, fluids that look like this. So in other words, if you apply a small shear stress to it, it won't deform at all. And typical thixotropic fluids would be things like drilling muds that you have in holes to keep the borehole open as you're drilling wells for water supply or for gas wells, oil or gas wells. And only once you increase the shear stress above some critical threshold, this amount, do you get it moving. It won't move until you do that. Once it moves, then it keeps on moving. So this would be what we'd call a thixotropic. Thixotropic. The fluids that we'll deal with in this class are exclusively Newtonian. So we'll always use Newton's law of viscosity, which is this term here. So that's basically it just defines a linear relationship between the stress that you have to apply to this plate and the velocity that you get in shearing. And so something that has a high viscosity would be would have a large dynamic viscosity. It would be something like honey, I suppose, or treacle, which probably isn't Newtonian, but you get the idea. Something which has a lower viscosity would be water. Something with an even lower viscosity would be a gas. If you look at the properties of different fluids, try and make this a bit smaller. So this is just a typical plot of viscosities for different fluids. Liquids are here, and so I think water is exactly at this location. This is water here. If you look at 20 degrees centigrade, where we are now at room temperature, then the viscosity of water, if I take a break, did I stop it or did I think I just continued it? So 10 minutes in, still not much going on. You don't think it's moving? Yeah, it's on 16 minutes at the bottom, yeah? It's on 10 minutes 56 at the bottom. Doesn't look like it's moving because it's not changing much, right? So I think it's moving. So anyway, viscosities. So a good number to remember for viscosity of water is something that for water is something like 10 to the minus 3 Pascal seconds at 20 degrees centigrade. You notice that as you increase the temperature of water, the viscosity goes down. It becomes less viscous. It flows more easily, in other words, as you warm it up, as you might expect. Gases behave in the opposite way. If you look at air, then as you increase the temperature, the viscosity goes up. It becomes less easy to shear because there are more collisions occurring within the system. And a good number for a typical gas for viscosity is something like 10 to the minus 5 Pascal seconds. Just the fact that it's 2 orders of magnitude smaller than for water, and the behavior of the two is different. And so those are useful numbers to remember. There's an example, I guess, in the notes. I don't know if it's worthwhile going through or not. I guess we probably have some time to do it. Just to, part of the core of this class, I think, is understanding how to set up problems in your own mind. And this, so this is just a problem that has a plate that's being dragged through a fluid. The plate goes through at some given velocity. The fluid has a viscosity in the overlying fluid, which is 1, a viscosity in the underlying fluid, which is 2 times the viscosity of the overlying fluid. And the question is, calculate the viscosities of the oils. So how would you do that? Well, you can write Newton's law of viscosity for the upper part of the plate, which you know is equal to the viscosity multiplied by the rate of shear times the thickness, right? This is the viscosity on the top plate due to the viscosity of fluid 1. This dy is equal to this thickness, right? So this is equal to 0.03 meters. So you have this, and you're pulling this through at the velocity, which is dy. So we have dvy is equal to 0.3 meters a second. I guess if we drew this picture of what's going on, this would be our velocities, right? It would look like this. And this would be our velocities in the other plate. They have to be the same velocities, right? So this would be our shearing velocities as we go down through the column. If we write the shearing stress on the base, T tau 2, this is going to be equal to viscosity of the second fluid, the same velocities and the same thicknesses as in the top. And we also know that mu2 is equal to 2 times mu1. So now, if we know that we can add these together, T1 plus tau 2, and we know this information, then we can write an expression in terms of these viscosities. We can write it completely in terms of viscosity 1 plus 2 times viscosity 1, which is this one, multiplied by the same shearing rates, which is equal to dvx over dy. Hopefully that is on. Is that on the screen, by the way? Thank you. 15 minutes in. See something on the breakwater, right? Out here, if I make it large. So you see something going on. You see some boats rocking a little bit in the harbor, but still not very much after 15 minutes. And so we'll come back to that. We'll still get it before the end of class, I think. And so now, if we know what the stresses or forces that we have to apply to this plate, and so the force that we have to apply divided by the area of the plate has to be equal to tau 1 plus tau 2. And so we need to know this force. If we know the force in the area of the plate, then we have this left-hand side. If we know that the velocity is 0.3 of a meter a second and the dimensions are 0.03 meters, then we have everything except for 3 times mu1, which we can solve for, and divide it by 3, and we get the viscosity of the oil. So I think one of the big challenges in this class is in being able to take a problem and imagine exactly what it should look like. And so I'm not sure how I can teach you to do that. I think you should have seen that, of course, in some of your earlier physics-like classes. Okay? All right, so zipping back to this, we have a couple more things to do. We talked about vapor pressure and surface tension. So vapor pressure. Probably the easiest way to talk about that is in the context of a phase diagram, which we kind of briefly introduced in class on Wednesday. And so we know that fluids, liquid or gases, exist at those two states, or solid for that matter. We know that at room temperature, water is liquid, but if we change the temperature by increasing it, we will boil it at roughly 100 degrees centigrade at atmospheric pressure. We sit at 1 atmosphere. But we can also, the other option we have is we could also change it by keeping it at the same temperature, but by reducing the pressure. And if we reduce the pressure, then as we get close to absolute vacuum, zero absolute pressure, then we'll find out that we actually are able to vaporize water itself. So we can do that either by changing temperature alone, by changing pressure alone, or by any combination of those. And this boundary between the liquid water and the vapor defines basically what the vapor pressure is. So vapor pressure is the pressure at which you transform from being water to vapor. In other words, no longer is there an equilibrium between the same number of molecules joining the water as leaving the water as vapor. There's a disconnection in that. And as you vaporize things, more molecules are vaporizing rather than condensing in the system. It's just a lack of that equilibrium. And so that defines exactly what the vapor pressure is at that particular temperature. So if you choose any particular temperature, say it's 50 degrees centigrade, then the vapor pressure is given by that connection with that curve. And of course, as we'll learn in the next week, as you go up in the atmosphere, there's less air on top of you, which weighs 1 kilogram per cubic meter. And so as you go up in the atmosphere, there's less material above you that you're carrying on your shoulders, so the pressure goes down. And so, the party trick of does it take longer to cook something on Everest than it does at sea level? On Everest, you'll be at a lower pressure, and so the boiling point of water will be less than 100 degrees centigrade. And so if you're relying on something to get to 100 degrees centigrade to cook, you can only get maybe to 80 degrees centigrade on Everest. So by definition, it'll take longer to cook something to the same degree as you get higher in the atmosphere. So vapor pressure is important. The other thing that relates to this class, and we showed the video earlier on of condensation above the airfoil of a wing, is if you look at propellers turn quickly, and in the same way that a wing develops lift, low pressure, you develop low pressure on the faces of a propeller, and you can cause the water to fail in tension, bubbles to develop. If you develop bubbles, those bubbles can actually rip off the brass from the propeller and destroy it. And if you look at, for instance, quiet submarines, the propellers, or the ship's screws, I guess, on those boats are huge. They're like the propellers on planes. And that's because they turn very slowly, so they have very low, they don't change the pressure very much. They have a very low chance of making bubbles. And if they don't make bubbles, you can't hear them, so they can run silently. And so submarines avoid cavitation, failure in tension of water, which is making bubbles. And of course, making bubbles by low pressure is exactly the same as boiling a pot of water, where bubbles come out by overboiling it. 20 minutes going on. You see something going on now. Take 2 seconds to go back to see what's going on. So this is a river which was next to the parking garage, which all of a sudden now, instead of flowing from right to left out to sea, has this wave which is now just pushing inexorably up the river and carrying with it everything that it carries with it. It'll start carrying houses, it'll start overrunning the quay, and it'll start carrying everything up. And so tsunamis are not like, as I say, like the wave in Portugal, a breaking wave that arrives on shore, but it's just this inexorable push of water that it goes up onshore, just like a very high rising tide, moving basically at the same rate that a tide would come in as well. Okay, I'm going to keep that running in the background, and enough on vapor pressures maybe. So the last thing for us to deal with is to talk about interfacial tension. And for that, I have this video in the background. Let's get this running. The vinometer. So when you're out on Thirsty Thursday and you want to see what the alcohol content is of your beer, or with friends, and of course you can't drink because you're still friends, you can put it in a vinometer. Vinometer is just
Same
something
setting,
that
right?
gives you the alcohol content of liquids.
Maybe
And so what you do
maybe a
is
few
you
years ago.
put the liquid in here, like water, I put it in. It fills up this little capsule at the top. This is a capillary tube which has, you can see the hole through it, which comes out at the bottom. You blow until water comes out of the bottom, so you fill up this capillary tube, and then you stand it upside down. You stand it upside down, and now this is open, and you can look within this tube, it's graduated on the side, to give you the alcohol content, which is the height to which this will stand up within this tube. And so it's really controlled by the surface tension, which will be across the top of this tube, open at the bottom here, which is at atmospheric pressure, and so it's a direct analog to the system that we'll look at right now.
The end. So I need to get rid of that. I need to open this up, I think. No, yeah, it is in here. So interfacial tension. Maybe I don't want to use these notes. I'll just draw something else out. Yeah, this is basic idea. So if you look at pushing a capillary tube into water, then what will happen is that water will rise up in this, being dragged by interfacial tension, the connection of the fluid on the side of the tube. Fluids that are water wet, so water wets glass, it loves to cover it over. But some fluids or some surfaces are hydrophobic. So this is hydrophilic, loves water. Mercury, well, it's not hydro anymore because it's not water. But this does not wet the fluid, and if you push it into the mercury, you'll see that it's inverted in the same way that this column is elevated. So this is the elevation of the fluids in both of these cases. Water rises, mercury is depressed, and the mechanism by which that occurs is by surface tension. So one question we might have is, how do we calculate what the height rise is within this? You see mayhem going on in Kamaishi on the right-hand side. How do we calculate exactly what this magnitude is? So if we look at surface tension, I'm going to stop it now. Don't need it. And I don't want to look at it again. And so the idea is that if you have a capillary tube, you put it into a fluid. The fluid initially exists here, and then it rises to some height that we'll call h. This has some diameter that we'll call d. And what we'd like to do is be able to calculate exactly why that gets carried out here. If we look at the pressure on this free surface, we know it's atmospheric, what we feel now. What we'll learn next week is that if we can connect that fluid pressure by a pathway to the same elevation within the tube, the fluid pressure at this point has to be exactly the same at this point. So that means that we can physically cut this column off and think of it as a column that is standing on its own. So we've isolated this tube. It still has this same diameter d.
and this same height h. But now it's being held up by some forces which are only on this boundary that we can think of as being t, and we can think of this as being t cosine alpha, if this angle is alpha. And so we can do a force balance between the forces that are pulling this up, which are going to be interfacial tension multiplied by the circumference, pi d, actually times cosine alpha. So if you look at this ring of forces here, the circumference is pi d, the magnitude of this force is sigma, and the component of it going upwards, because it's actually at an angle, is cosine alpha. The force balance going down is just the weight, because we've cut this physically off here. The weight is going to be the volume times the density of water times gravity, which is the same. The volume is going to be pi d squared upon 4, and the height, and rho g. And if we equate those, we end up with an equation which is interfacial tension pi diameter cosine alpha is equal to this term, is pi d squared upon 4 times the height times rho g. Remove one of the diameters, remove pi, and solve for the height, and the height is equal to interfacial tension, the angle it makes, which we can assume cosine alpha is equal to 1, multiplied by 4 and divided by density and gravity. So the height rise is controlled by interfacial tension and the density of the fluid and the planet that you're on, and also this to some degree. And so coming back to the venometer, if the density and the interfacial tension of the mixture of water and alcohol, which of course beer is, spirits are 70%, beer is perhaps 5%, 10% now these days, wine is perhaps 15%. If the interfacial tension and the density of those liquids are a function of alcohol content, you can calibrate this height rise to be able to define alcohol content in the venometer. And so that's one useful application, if you like, of surface tension. Surface tension, of course, is the same thing that bugs walk across the surfaces of water with as well. Okay? So, well, we reached our goals. We talked about those 4 things today. Next week, we'll talk about pressures in fluids